Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, Stand 3 and beyond. So the first thing that we're going to do, we're currently at release 2.4, and we're not done with the number 2 releases yet. There'll probably be a couple more releases before Stand 3 comes out, but this will be the third time. We did a major refactoring with Stand 2 to try to not change any functionality, but actually clean up the code underneath, which is really important if you want to maintain a big project going forward, to take things out as much as you put things in. Often people think the third time is the charm, and we're hoping that's true for us, that we'll get it right this time, but it'll probably keep evolving. One of our big goals here is removing duplicated code in the interfaces. Right now we have an underlying C++ API, and then a use of that from Python, from R, from other places. And we want to remove all the duplicated code we can there, just to make things more robust to changes and to keep everything in sync. And we want to minimize the dependencies we have right now. Right now we have this very fat dependency between our interfaces who kind of know everything about the internals of everything, and we're tightening that up with some more modularity. So we also want to be able to make a more modular user-facing C++ API to make it easier for people to do things like use our automatic differentiation, use our density libraries, and to make it easier to define interface APIs on top of the CPU. The design and some coding for this is underway right now, but it'll probably be 6 or 9 months, I think, before Stand 3 version rolls out.
Can I ask a question related
Sure.
to that? How modular are things like the whatever you're parsing the programs into, like the abstract syntax tree and the parser and stuff like that, like sort of the front end stuff?
I'm not sure what you mean. Like right now we're parsing into an abstract syntax tree that's basically boost variant based. That's a pretty lightweight thing that comes out of the boost spirit parser. So it's reusable, but it's kind of a pain with the callback methods. It's all nice and type safe, but it's like really insanely clever template programming and lazy evaluation inside of it. So it's using all sorts of crazy boost stuff. That's one of the things that causes compilation times to be so slow, is the deep template metaprogramming inside that comes out of Boost to deal with the parser.
So you already have 2 languages, right? So I mean, you have where you interface to. So, but you don't use Swig or something. So
No, I had never even heard of Swig until today, so I will go check it out because it sounds promising.
Yeah, because then you have tons of languages to interface to.
Mm-hmm. Yeah, so that sounds very promising. I didn't know anything about it. Which is one of the reasons to come to workshops like this. Too.
Like 10 years old.
I'm more than 10 years old. So.
I've heard that. It's very stable.
Yeah. Right. Yeah. No, there's a lot that I don't know. There are more things I don't know than I do know. Yeah.
I've heard that Swig is pretty hard to use and pretty picky on what works, what doesn't work,
Mm-hmm.
how you can make it work. So don't spend just small time, but maybe be ready to spend more time.
So maybe one way is to use some, and I think Heiko might be the key here. So maybe to reuse some of what Shogun has been doing
Mm-hmm.
to reuse these interface maps that took probably years until this worked in Shogun stably without memory leaks and everything. So maybe one can take some of that and put it into some other project.
Yeah, we're big believers in borrowing expertise, if not code. We'll borrow any code that we can manage to fit in too as well. So
I think it might actually be a possibility to extract all that interfacing from Shogun,
Mm-hmm.
remove all the content, right, and just have the interface stuff,
Yeah.
the shell released
Yeah.
as a separate thing.
yeah,
So
just getting a hello world that works is usually half the battle, and getting it compiled. Like C++ is just a nightmare compared to Java, which I did for the 10 previous years. The next thing that's actually going to roll out, because I hope to finish the final coding for it this weekend, is a differential equation solver. So a lot of models, climate models, pharmacokinetic models of drug transport, anything where your underlying model involves a differential equation that has parameters like a rate equation or something, and you take noisy measurements of it. Typically, people will build an ODE solver to solve systems of differential equations into the model. And you can think of that as just doing the same sort of work as the linear predictions in a linear model would be. And we've almost got this done. The big difficulty here was we had a prototype that we did in a big project with Novartis that automatically differentiated the integrator. So you solve these ODEs by integrating them, by basically simulating in time. You can automatically differentiate the integrator, but it's very inefficient and you can't control the errors on the derivatives. So what we need is we need to be able to take derivatives of the solutions to the differential equations with respect to the parameters. The right way to do that is to build a big coupled system of differential equations where you differentiate the system itself. And Michael Betancourt worked out all the math for us. We've got it all working. We've got a prototype working, and we've pretty much got it done. So this is going to come up soon, and we're working with Frederic Bois and Amy Racine-Poon and Sebastian Weber from Novartis and UTC in Paris on this.
So just out of curiosity, there's been all this interest in solving differential equations as probabilistic inference problems. And
Yeah, that's a separate issue.
It's kind of super amazing because you have all the tools kind of already in the toolbox.
Yeah, but we're not. That's not what we're. So you're thinking of like Girolami's thing that he's working on. Yeah, this is slightly different. We're actually doing traditional solutions of differential equations for which we have noisy measurements of outcomes of those differential equations. So we want to be able to fit the parameters. We want to build a statistical model, take noisy measurements, and fit the parameters of the differential equation system. So usually the kind of diffie-Q systems we're working with here aren't particularly difficult. So it's not like we're dealing with big hairy things. And this is only going to be for non-stiff equations. There's one more step of needing Jacobians and another coupling layer in order to get stiff diffie-Qs. But we're going to do that as well because there's uses for it. There's a system that already does this. PK Bugs does this already, except they don't have a gradient-based system, so it's a little easier for them. I don't actually know that much about PyMC, so I can't really answer that question, I'm afraid. I mean, maybe somebody else knows more about both systems from a...
So PyMC is based on Theano, which allows you to specify models from Python rather than having to write down a separate language.
Yep.
So it's a bit kind of easier to get your hands on. You have to do less stuff till you get your samples from the model. And they also do this Hamiltonian Monte Carlo, not sampling stuff, but so Stan is, I think, way more sophisticated in the way that you can have bounds on parameters, they do proper adaptation, these kind of things. Because PyMC is a lot is very young. The Auto-diff parts of it, at least.
Yeah, and we're specifically aiming at people who want to write in a little embedded language. Like most of our users are R users who don't know Python, but they're happy writing models in a kind of R-like syntax. But that's a different issue. We're certainly happy to help people build better adaptation and stuff for their HMC. The next thing we're going to do is higher order auto-diff. This should also be done. This is code complete being tested. The only holdup we have is we can't get Windows linker to link this thing without blowing out memory under any of the Windows compilers we have. So we may wind up rolling out higher order auto-diff for every platform but Windows because we can't make it actually work in C++ on Windows. Maybe some people here could like help us do that because you guys probably know how to make C++ work on Windows better. And we're probably not going to do all of our cumulative distribution functions. These things are the CDFs are a real monster to differentiate with respect to their parameters. They're easy to differentiate with respect to their outcome because you just get the density back, but differentiating like the beta distribution with respect to the alpha and beta parameters is much trickier. And we've got the first order stuff of that worked out, all the iterative algorithms, but the higher order stuff not yet. As soon as we get the higher order auto-diff, and that's all done, and we may just punt on the Windows testing if we can't get it to work because it validates on Linux and Mac already. As soon as that works, we've also got the Riemann manifold HMC already coded and ready to go. And the important part about this is it supports posterior inference where you have position-dependent curvature. So by position-dependent curvature, if you take a multivariate normal, no matter where you're at in the posterior, the covariance matrix is the same. If instead I do something like a hierarchical model where there's a hierarchical variance parameter and the value of that hierarchical variance parameter controls the scale of, say, the regression coefficients, then what happens is your covariance matrix changes depending on where you're at in the posterior. Right? The kind of adaptation we're doing in the basic Euclidean HMC is assuming that the posterior curvature is uniform everywhere. If that's not true, you need to really step the step size, really scale the step sizes down in order to get into the tails of the distributions. Riemann manifold HMC solves all of this at a high computational cost. We need to compute up to third order derivatives each iteration. And we need to do things like an eigen decomposition to smooth out the curvature to get good estimates of it. This is all done. You can read Michael Betancourt's archive papers. It's all implemented. He has a really sweet SoftAbs metric. So this isn't the same as the Girolami and Calderhead Fisher information matrix, which is based on an expectation. We're using the SoftAbs metric that Michael invented, which takes the Hessian, eigen decomposes it, sort of compresses the scale, makes everything positive definite by making all the eigenvalues positive, puts everything back together, and then it'll work in full generality. It's just going to be about 1,000 times slower per iteration, but this gets at, there's some problems that we simply can't fit without this method. So it may be slow per iteration, but there are things that this will be able to fit that we currently can't fit, and no one can fit. So this is very exciting, but not for all the usual big data reasons. We're also, there's another, Michael's writing papers, Michael Betancourt's writing papers faster than we can implement this stuff in Stan. He came up with a very nice physics principled thermodynamic sampler. So if you're used to how the current things like simulated annealing or tempering work, they're sort of forcing the physical system from the outside. This is physically motivated by applying something like a heat bath and letting the physics sort itself out. So this is going to be good for the same sorts of reasons as everything else. The same reasons as tempering and annealing is, so it'll be good with multimodal posteriors. Let me just, I see that I should whip through this. I had lots of questions, but okay. Well, we can stop now if you want. I mean, there's like 5 more slides, but we can stop it here because we're over time.
If there is a particularly important slide, then maybe...
No, I wouldn't say any of them are more important than any of the other ones.
Go through them very quickly.
Yeah, just hit space.
Okay, I'll just hit the titles. We're looking through ensemble MCMC methods. We're going to roll out marginal maximum likelihood so we can do point estimates of hierarchical models by marginalizing out the low-level parameters. We're going to, we have higher order derivatives, we're going to be able to do MLE and marginal maximum likelihood error estimates, which all the statisticians want. And then the 2 big things we're going to do is ALP here is working on variational Bayes. And we're going to build black box variational inference. This is all under development. I'm not, it's being prototyped right now. I'm not sure that we have an ETA on something like that because there's a lot of research to do with this. But the nice part is we'll be able to do batch and streaming. So this is our road to doing real Bayesian large-scale models. And we're also working on EP versions with a different set of collaborators, which is going to allow data parallelization, I think, in a lot more easy way than the stochastic methods are, at least from what we know.
Is there a
that was the last slide.
The word discrete is not in any of these slides?
Yes, because we don't do any discrete sampling whatsoever.
There's no plans to do this at all?
We don't really know how to do it.
Okay.
We can't take our language and easily find so like with a directed graphic modeling language like bugs or something, it's very easy to find the Markov blanket of everything. Since we have this imperative way of specifying the log probability, there's no easy way to pull out the conditional probabilities. The best thought we have now is we have the user separately specify conditional probabilities, which is like really ugly, or we create a limited representation language, more like bugs or JAGs, where we can do all the computations that we need. If anybody has better ideas how to do that, the only reason it's not on our schedule is we don't have a satisfying way to approach it. And most of the problems we deal with marginalizing out the discrete parameters is better than sampling them anyway, although it's a bit of pain for users. So.
Thank you for coming.
No parting wisdom for us?
forth and do good things.